Morning, guys. We're going to finish off with two last lessons in this energetics chapter. So far, this whole chapter here has been focusing on a guy called enthalpy change. It's the heat energy in the system. We've been saying that it's impossible to measure the absolute enthalpy. There's way too many particles. There's way too many ways energy can be stored before and after. But fortunately for us, we're looking at the change over the course of the reaction. We want to see overall endo is the heat term on the left-hand side, or exo is the heat term on the right-hand side, along with how do we actually calculate the delta H. So what I put together for you here, because we had 7 different ways of finding delta H, I put together a formula sheet here. No, unfortunately, you can't use this on any quiz or test, but it just serves as a nice summary of the reactions, some of the assumptions that go into each of these ones. Hopefully, it'll help you out. So I'm going to post a link to this here on our shared Google Doc here. We had enthalpy change, like I just mentioned. Anytime you have this not symbol, it means to do the pure, most stable allotrope. 1 bar pressure, it usually is at 25 degrees. We had, like I mentioned, these 7 different ways. Specifically, the last 2 that we talked about focused on ionic compounds, the last 2 lessons. A couple important notes for you here. Calorimetry, this one here was your experimental way. This one here was, let's go from a temperature change here from the thermometer, and let's backtrack and let's figure out delta H. We then did bond enthalpies here. Towards the bottom of the table, I actually show you where all the numbers can be found as well. Bond enthalpies, although we are still trying to find delta H, which is enthalpy of products minus enthalpy of reactants, it was just in the Hess's law, in the enthalpy cycle, we saw that the terms had actually switched positions. So by doing reactants minus products, sometimes they say broken minus formed, that actually helps us find the delta H. Hess's law here was what we actually applied for the remaining. Right? Hess's law by itself was giving you a bunch of mini equations. If I add up those mini equations, the delta H is add. If I end up scaling the equations, multiply 2, the delta H scales. If I divide by 5, the delta H scales. If I flip the equation, what would have been endothermic one way is now going to be exothermic the other way. So the sign of delta H actually flips. And then we saw, even though that method works, having to deal with all those mini steps here, playing around with them, who has the time to look through tables and tables of these mini equations? So what we did is, instead, we define what was called a formation equation. Make sure you know how to define these ones. This is making 1 mole of compound from the pure elements. And then we found we were able to find the delta H of any reaction. If you use formation numbers, it was products minus reactants. If you use the combustion detour instead, it was reactants minus products. That is able to give you a delta H of anything. It's best, we did that one question, it's best if you're trying to use formation numbers that the equation that you're asked for is not formation. You're going to get a true statement. You'll get something like x equals x. It just doesn't help you solve anything. For an element, because elements are the simplest it can get, so the formation of element is 0. However, the combustion of element is typically not 0. The one exception here is the heat of combustion for oxygen. Oxygen doesn't burn, so this one here is 0. But aside from that, other things burn. Hydrogen burns, carbon burns, so those ones are not necessarily 0. Born-Haber cycle was that very scary diagram. Whether they say construct a Born-Haber cycle or not, I would start there. I would start off with sort of the solid here. I would have the gas ions. I would start off with the lattice enthalpy, which is a big equation, and I get slowly work your way around. I need to undo the formation. I need to atomize both of them, ionize. Most of these are endothermic. Most of these require an input of energy. The only one that has the opposite sign here is the electron affinity of the nonmetal. That tends to be exothermic. So that tends to have a different sign than the other 3. We also switched over because we're not given atomizations anywhere on the data booklet. Sometimes, especially for a diatomic compound, it's nice a diatomic compound like chlorine is already in the gas state. All we're having to do to atomize it is we're just having to rip it apart. So sometimes we can actually approximate the atomization as half the bond enthalpy. Otherwise, they're going to give you all the other arrows and actually ask you for atomization. Dissolution we ended off with last day here. Don't get scared over this X, N, Y, M. It's a little bit easier when they actually give you the compound. But pretty much dissolution is, let's break everything apart, let's melt the thing, but then let's surround it with water. The breaking apart will always be very endothermic. It's a huge upfront cost, but because I do get a lot of stability, a lot of the energy back when water actually surrounds the ions, overall the solution enthalpy might sometimes be positive or negative. Right? There's a sample picture of a dissolution cycle here if you like. So we have this one. Solution enthalpy here, there again, using lattice enthalpy is going downwards. You can just cross out that negative to just say lattice enthalpy is just going to the gas ions. That takes you higher energy endothermic, negative exothermic when water surrounds it. Depending on which is bigger, it at least lessens this upfront cost and makes the reaction more doable. Where can you find some of these data numbers here? I gave you, you can basically flip your way through, you don't need to memorize this, but you have some equations like MCAT. We're going to see this formula in this lesson and the next lesson here. Some constants we see in section 2. We saw that first ionization electron affinity was useful for Born-Haber cycles, so a BH cycle. If I looked at bond length or bond enthalpy here, that's on table number 11. For formation data, it was table number 12, combustion table 13, and then we did some of that lattice stuff here, 18, 19, 20. So again, don't memorize that. You always have your data booklet, but that's where you can find some of the numbers. Today, what we're going to do is we're going to switch over and we're going to talk about a guy called entropy. Turns out enthalpy and entropy are sort of two halves of the story. Although we spent a good almost 2 weeks worth of lessons here on enthalpy, we're only going to spend like a half lesson on entropy, and then by putting these two things together, we're going to see how does enthalpy, how does like the heat conversation and the entropy conversation, which is the randomness contribution, how do they both factor into something called free energy in predicting whether reactions occur or not. So even though entropy is very important, turns out there's not too much to talk about it. So let me just introduce to you entropy, and we'll go from there. We will be using table 12 later on as well, but let's just start off here. Let's start off a fresh section here. This guy here is called entropy. For some reason, we use capital S for it. Let's start off with the definition first here. Entropy is defined as the measure of disorder in the system. Some other words associated with disorder, sometimes they call entropy the amount of randomness. Sometimes they say how much chaos is in the system. Basically, entropy is disorder. The more chaos, the more random the system, the higher the entropy is. It does have something to do with energy. We're going to use this very loosely here. Entropy here, it sort of measures the number of ways energy can be distributed. We're going to refer to like the number of ways here as different microstates, different sort of ways the system can look like. What I want to show you in that here is entropy does have something to do with energy, but it does sort of represent energy as a microstate. It's sort of energy that's sort of locked away, and we're going to see that in these upcoming examples. So let me just start off with a quick analogy here. Let's imagine I was standing on the top of the hill. So here's me. Let's imagine I had 3 basketballs, and I had these basketballs here painted. So half the basketball is painted. In this case here, when you look at the basketballs, I would say, oh, perfect. These basketballs are nicely side by side. We're in a nice ordered orientation. Because entropy is defined as disorder, I can say this one here is relatively low disorder, right? It's ordered. It's nice and patterned and nice, and everything is painted side down. Everything looks nice. What I'm going to do is I'm going to just, in my experiment, roll these basketballs down. What are the chances that these 3 basketballs here, when they sort of land, what are the chances that they're going to land painted side up, right? What's the chances of this? You would say here, well, not very likely, right? There are 3 random balls. They roll different distances here. They might bump into different things along the road here. Very unlikely it's going to be this. It's more likely that one of the balls might be like this, and the other ball may be like that, the other ball like that, or another orientation, maybe this way, maybe this way, right? There's a whole bunch of different combinations that we might manage. However, if I ask you the same question, what are the chances of getting exactly this, right? Exactly the first ball have this orientation, the second ball this one, it's also equally unlikely. It's just that I wouldn't even take another look. I would be able to see when it's ordered, when it has all paint side down or paint side up. There's a whole bunch of ways I can set up the system here. I would just say, well, these are just some sort of chaotic combinations. And I wouldn't even take another look. I'd just say, yeah, it's probably going to land in one of those states. It's not that any given state is any more likely. It's equally unlikely for it to get an exact match of the one that I drew, but because there's so many ways that I would just classify as being chaotic, we naturally in nature tend to go from a case that's ordered to a case that's more chaotic. More disorder here means a higher entropy. And we're going to actually see this in the second law of thermodynamics later on. Nature does always tend to higher chaos. We can sort of determine the chaos. The easiest way here is to take a look at the state of matter that we're in. So we want to see sort of how the system can actually show this chaos. So we start off here with the solids. Solids, the particles don't have much energy. They're sort of locked away. They're sort of side by side. They're just shaking in place here. This one here, like the basketball analogy here, this is a really, really orderly situation. Very low entropy. As I heat things up, however, let's say I heat it up beyond the melting point here, those same particles here, they start moving a little bit faster. They start overcoming those intermolecular forces. As I get to sort of liquids or even aqueous, right? Those ones there, how is an aqueous different from a liquid? Liquid would usually be pure. Aqueous would usually imply that there's other things that are dissolved in it. We're going to see that in general, when you have mixtures, you can make more of a mess. So liquid and aqueous are sort of similar. Those I would expect to be higher entropy, much higher than a solid. They're sort of not locked away. And then the one that actually gives me the most entropy, the most chaos here is the gas. In the gas state here, the particles are just really wildly separated. They're really far apart. They're zipping around all over the place here. Gases are really chaotic. The number of ways these gas particles can arrange itself here, there's many more combinations. I would gradually have gone from an orderly low entropy case here to a case of really high disorder. And in this case here, it's high entropy. So yes, entropy does have something to do with energy, but it represents an energy that's locked away. As I'm a solid, when I look like this, how much energy is locked away when I look like this? Or as a gas, when I have many different combinations, many different orientations, I could be on this side or that side, many different ways I can set up the system. Again, the entropy would be higher, the chaos is higher, and the energy that's locked away in that state here is actually higher. So that actually gives rise to the first style of question they can ask you, is they can just ask you, as an example here, I want you to predict the sign of delta S, right? And in general, when you see delta, you think final minus initial. For us, again, final is always products minus reactants. So although there were a lot of formulas you saw on that formula sheet here, I just tell people memorize everything as products minus reactants. The only two times that we saw it was reactants minus products, even though on the left-hand side, we're still comparing final and initial, the only two times that it switched was bond enthalpy was reactants minus products, and combustion was reactant numbers minus product numbers. But nonetheless, it gave you the overall delta H going from reactants to products. So in terms of predicting the sign, what we're going to do is we're going to look at the state of matter. So let's start off here. Carbon starts off as a solid. Oxygen starts off as a gas. Let's say this one here burns to produce carbon dioxide. What you're going to do is you're going to look for the most random phase on either side. So in this case here, let me actually dramatize this a little bit. Let's say this one here is a liquid oxygen. It's sort of weird state. We're not at standard conditions anymore. So what we're going to do is we're going to look for the most random state on either side. On the left-hand side, I know I have a solid. I know I have a liquid. In this case here, my liquid is the most random phase. Ignore the solid for now. On the right-hand side, CO2 is actually a gas. So gas is the most random phase. And in this case, when I go from a sort of moderate entropy case to a more chaotic state, I would have a very big number at the end. I would end up getting an entropy change here. Be used to this notation here, the greater than symbol here, or you can just say in words here, the entropy change here is positive. In words here, I'm saying we go from, if oxygen was a liquid, I'm just going to dramatize that. So liquid here, it goes from a sort of medium order, or let's just say disorder, just for simplicity, medium amount of chaos to really high amount of chaos, high disorder, so therefore the entropy has increased. Delta S positive actually means we've gotten more messy. And that's actually the way we're going to see nature wants to go. What if, however, the most random state was actually the same on both sides? So what if we did the Haber process? N2 gas, 3H2 gas. This is an equation for you to memorize. This becomes 2NH3 gas. The catalyst here is iron. We do this a lot. Again, same argument. Can you predict for me what the delta S is likely to be? So we look for the most random phase. The most random phase on both sides is actually gas. And yet this time what we're going to do is we're going to look for the higher number. If I have more number, in this case here in total I have 1, 2, 3, 4 moles, right, by ratio. For every 4 moles of gas reactants, as they become products, they only become 2 moles of gas. Can I make more of a mess with 4 particles or with 2? Imagine going to your rooms and you have 4 shirts. I can toss these 4 shirts around or just toss 2 shirts. You would say the more shirts that I have, the more chaotic it is. I would expect, even though gases is the most random state on both sides, I would expect this one here to be more chaotic. Whereas the other side, even though I can still make quite a big mess because it's a gas, not as big a mess as before. So I go from very chaotic to not as chaotic, so I'd expect the delta S less than equal to 0, or again, just in words here, delta S here actually being negative. So that's sort of the first style of question here. The note here is we're looking for more particles in the most random phase. So in the first case here, when I switched oxygen to a liquid, the most random phase here was a gas, so I get more messy. Entropy change is positive. In this case here, even though it was the same on both sides, I could argue if the numbers are different, the more particles I have, the more chaotic that side is. Sometimes on a paper 1 question, they do ask you, what if it's similar? What if this oxygen was normally like a gas? If I had 1 gas and 1 gas, you'd say the entropy change is roughly the same. So it's possible that it's close to 0. Entropy, it turns out to be a value that's really, really hard to measure. So even though I'm going to tell you, you can find these entropies here on table number 12, you're going to find that there's a lot of missing entries. Because if you imagine here, same sort of problem with enthalpy. There's way too many particles. There's way too many ways, not just of storing energy. There's way too many ways I can look alike. I can actually all be on one side of the container, or half can be on this side and half can be on this side. I can be moving at different speeds here. There's way too many ways this order can be done in the system. So unless you really, really simplify the system, entropy is a really hard number to measure. Let me just show you on table number 12, entropy is actually measured. It does have some energy dependence, so we'll come back to that later on. So it does represent some energy, but again, it's energy that's locked away. It's only in joules, however. When we do enthalpy, it was kilojoules. When we do free energy towards the end of this lesson, also going to be kilojoules. Entropy is actually very small in the grand scheme of things. Entropy, however, also has some temperature dependence. We definitely see if I heat things up enough to actually melt it, obviously entropy changes. But even if I heat it up and it hasn't yet reached the melting point here, as the particles start vibrating a little bit harder, they get a little bit out of order, they get a little bit more ways to sort themselves out, so it will have some temperature dependence, although it is also quoted per mole. So joule per Kelvin mole. I mentioned this number here is very, very hard to measure, but let me just give you some values that they have. We're going to have the entropy of ice, so water as a solid, the amount of chaos that's locked away, the energy that's locked away in these microstates here, 48 joule per Kelvin mole. When water is a liquid, so H2O, it's now 70 joule per Kelvin mole. When entropy here of water as a gas, so steam, it now has 189. Notice, although I'm not necessarily sure how they got these numbers here, at least it follows our trend. As I go from solid more so to the gas state here, our entropy increases. And again, the emphasis there, entropy increases even as temperature increases in general. You'll notice I've added in on the table here, there's that not symbol. Make sure you know again, what does that not symbol mean? That not symbol here implies that we are at standard state. We want to be tabulating numbers so I can make a fair comparison between the compounds. I don't want one to be super hot and one to be high pressure, low temperature. It's really hard to compare. So the standard states I'm talking about, remember in all this stuff here, we're doing 25 degrees, or you can say 298 Kelvin. In terms of pressure, you can be 1 bar, that's 100 kilopascals. If we're solutions later on, 1 molar. Again, I'd be like saying 1 mole per dm cubed like that. But we want to be sort of these standard conditions so it's fair. This is nice because this is our regular exposure of these ones here. How does water usually appear when it's under roughly 1 bar pressure, 1 atmosphere at room temperature? Well, water is a liquid, right? So I would expect, I don't know how they did the exact experiment, but they figured out the amount of chaos that water has at 25 degrees at the regular exposure, 1 bar pressure, it's 70. how did they manage to get a standard state for ice, standard state for steam, when water isn't solid or gas at this temperature? As you might imagine here, there is some extrapolating involved. Again, I don't know necessarily how their experiment was, but they would be under these standard conditions. We know under these standard conditions at 0 degrees, that's when ice switches over to become liquid. What they would have done is they would have figured out what's the entropy of ice here at the temperatures when water actually is ice. And then what they do is, oh, you want the standard state one to compare. I'm going to extrapolate that trend. I'm going to say if water remained to be ice and if it continued on, it would have been roughly extrapolated that. Even though I know the real water actually is, as a liquid, it's actually a higher entropy. So there is a little bit of extrapolation involved here. Just watch out for that. It's just so that I can make a comparison between the two of them. One other technical note here, not super obvious. Let me just sketch up for you table number 12. Right. You can look at it for more detail later on. Table number 12 here, earlier we were using them for formation data. Right? So you have a handful of compounds going down the side. You had a few different columns. So far, we've only used one column, which is the heat of formation. For this lesson, we're going to actually use the last column. For those very same compounds that you had from earlier, you don't need to just look at the first column. You can look at the third column over. Again, you're going to be missing a lot of blanks. Entropy in general is really hard to measure. You're going to be actually trying to match up, well, what is the entropy for these chemicals? I mentioned the comment on units here. The enthalpy change here is going to be kilojoules per mole. That's going to be humongous. In comparison to the energy that's locked away in this disorder, this is only joule per Kelvin mole. The entropy term, as we'll see towards the end of this lesson, it does need to get helped up by temperature. It's going to eventually get us a guy called Gibbs free energy of formation. The Gibbs free energy of formation is similarly in kilojoules per mole, so only entropy is weird, it's joules per Kelvin mole. What may not be super obvious, however, right? Sure, I can just read the table here. So far, you'll notice that these ones here are all delta H's or delta F's. That means these ones here are relative enthalpies, or relative free energies we'll get into with G. Whereas for S, you notice that there is no delta symbol. There's actually a really technical note here. When there's no delta, it means that these ones here are actually exact entropies. So they've asked on the old IB exam question, how come for enthalpy, I needed to use these relative values, I needed to set reference points there arbitrarily, whereas how come entropies, how come this disorder actually is an exact number and it'll always be this number? Here we're going to get to another law of thermodynamics. So far we've done the first law of thermodynamics was energy conservation. Let's switch over to the third law of thermodynamics. So third law of thermodynamics. Seems like a waste to just do a law on entropy, but it's okay. In science, whenever we have something that's proven as a law, it's been tested time and time again. And here what we're going to do, the third law is the entropy of a perfectly ordered crystal at 0 Kelvin. The entropy of a perfectly ordered crystal at 0 Kelvin is exactly, it's absolutely 0 joule per Kelvin mole. So let's see what that says there. We're going to start off with a crystal. If anyone were to have entropy 0, disorder 0, we would imagine in terms of the states, I would imagine that we're looking at a solid. Because solids, they really aren't spreading through the container, they're not slipping and sliding, they're not making a big mess. Solids are nice and orderly, but if you take a look at any old solid, usually we're going to be at some room temperature, usually it is still going to be vibrating in place, usually it is still going to cause a little bit of disorder, a little bit of chaos, not a lot. But what we're going to do is we're going to steadily cool this down, we're going to steadily steal away the kinetic energy. So therefore, the particles themselves can't shake anymore. And as they become a little bit more sluggish, they start getting frozen in place. If I can reach a theoretical 0 Kelvin, and we slowed it down in such a fashion that the particles were perfectly lined up with each other, there's also no guarantee of that, because lattices have so many different bonds here, it's possible one of the particles may actually slide into the gaps. So hard to control. But since this is just an assumption anyways, we're going to assume we pulled away the energy so orderly that this is a perfectly ordered crystal. Just means it's nicely arranged, and at 0 Kelvin we have perfect order, there's no chaos. This is the one way to organize the system. So in this case here, this is a perfectly ordered system. That's why we define entropy as disorder. If we're ordered, it means our disorder is 0. I can then say absolutely the entropy is 0. and I'm just going to remind your units are joule per Kelvin mole. Because there is an absolute 0 point, there is an absolute perfect order point, all my other entropies are in relation to this reference. In relation to comparing it to that chemical's crystal when it's perfectly ordered, these ones here are now going to be exact entropies. These ones here are not an arbitrary reference because I have a perfect level point, I have a perfect 0 point. Enthalpy and free energy are not the same. For enthalpy, we arbitrarily came along. We had defined what it meant to be a formation. Some arbitrary references we said was, what's the enthalpy of formation element? Oh, let's just call that 0, right? Let's just pretend elements are as simple as they can, and yet we know elements themselves are actually made out of subatomic particles. There is some amount of stored energy. There is some amount of heat inside the system as well. We just set an arbitrary reference of 0, and then based on that arbitrary reference, all our numbers are now relative to that arbitrary reference. Analogy would be, let's say I asked you, how far, what's my elevation right now? We would naturally say, well, from sea level, right? Let's say the sea level is here. Let's say the ground is here. Naturally, I would say, well, sea level seems like a good 0 point. I can figure out my elevation above that sea level. Fine. But what if I came along and I reset that 0? You didn't have to set the 0 height at sea level. You could actually say, well, what if I actually look at the entire Earth? What if I measure to the center of the Earth here? Suddenly, all your numbers are now going to be different. And that's why, depending on wherever I set my references, like setting the reference for formation of element as 0, it will make my numbers show a certain value. If you later on redefine that reference, all my values will change. Fortunately for us, the thing that saves the day is we're not necessarily interested in just the enthalpy by itself. We're interested in the change. So while the numbers themselves might change, at least the difference itself doesn't change. So just be careful of that. They have asked before, why does entropy doesn't have that delta here? Why is it absolute? It's because we have this third law of thermodynamics. So let's just try out a question here. Entropy, calculate. This time I want you to calculate entropy. When I'm looking at change, there is a change here because I'm looking at products minus reactants, but you notice that in our formula, it is going to be an absolute entropy. There's no delta there. It's not relative, but I still want to go as it changes from products to reactants. So that's why it is still in the question, right? What's the delta S? What's the change as reactants become products? And yet we see that these ones here are absolute. So I'm going to give you a sample equation here. Let's give you CH4 as a gas, 2O2 as a gas, becomes CO2 as a gas, and 2 water. This one here is written as combustion, so it's best to say water is a liquid. We want to do this all at standard state anyways. Fairly simply then, we're just going to try to find the entropy change. The change in entropy is final minus initial. Because entropy is also going to be quoted per mole, we saw that joule per Kelvin mole. If I just have a 1 ratio here, I'm going to take the entropy of CO2 as a gas. I do want to include the state because depending on the state, I may have different chaos. I want to do twice the entropy change of water as a liquid. And then I'm going to minus off what's the entropy change of methane, CH4 as a gas. And then I'm going to go twice the entropy change of water, of oxygen as a gas. Where can you find these entropies, right? So far, I mentioned you can find them on table number 12. So let me just scroll up on table number 12 here. I'll copy them down in a second. So if you look at table number 12, so far we've used this table already for heats of formation. This time for those same compounds like methane, I'm going to use the entropy column. You'll notice it is just joules, right? It's 1,000 times smaller than the other two, and we're going to see that's why it needs to get helped out later on. Lots of missing gaps here because entropy in general is really hard to measure. When you actually do water, be careful. Water is given to you as both the liquid and the gas state. For a combustion reaction, we always assume liquid, so we're going to use 70 instead. So looking at that table there, I do actually need to give you one. I'm not actually going to find oxygen on that table, so I'm actually going to give you one more value here. Given the entropy change of oxygen, I'm going to give you that one as 205 joule per Kelvin mole. So try it out for yourself here and double check my numbers when you're using the table. I was getting earlier 213.8. That's the amount of entropy for CO2, joule per Kelvin mole. I need to double water's value. I mentioned I'm going to use the liquid value, so 70, minus off the entropy for methane, which is a 186, and add twice the value when they gave you for oxygen as well, 205. I could be able to make a prediction here. I'm going from the most random phase here being there are 3 moles of gas. I want to go over to the other side here. The most random phase is gas, but I only have 1 mole of gas. I would expect the delta S to be less than 0, to be negative. Let's actually crunch through the numbers and actually see what we get. 213.8 plus 2 times 70 minus 186 minus 2 times 205 gives me negative 242. And again, for sig figs here, because throughout this chapter we're just doing a simple plus and minus, we're just having to line up the decimal place. The units are going to be joule per Kelvin mole, because that's what the table had them in. In this case here, they're going to always ask you questions. Well, what does it mean if this guy here is negative? Up to this point, we've just been doing delta H. Negative meant exo. This time we're talking about an entropy change being negative. Entropy is chaos. Entropy is the amount of disorder. So we're actually getting less disorder. Almost like a double negative there. So we're actually getting more orderly. It's not as easy to make a mess with 1 mole of gas versus, say, 3 moles of gas. Right? So that's a very common sort of paper 1 style question. Just predict for me, is it going to be a higher entropy or a lower entropy? I'm just going to hint at the very last concept in today's lesson, and we'll flesh it out somewhere in tomorrow's lesson. We're going to be looking finally at a guy called spontaneity. I want to know whether reactions happen as written and why some reactions don't occur at all. So when something is spontaneous, it just occurs. So let me just make a definition here. A spontaneous reaction, the reactions occur without any external influence. So you mix these reactants, you put them in a container together, and they start combining, or they start replacing each other. And they just happen without you necessarily doing anything. We're going to learn in grade 12, all reactions require some energy input. So this is not completely isolated. So this one here is, we're going to assume there is that energy input. But somehow the particles can steal enough energy to spark the reaction, to get the reaction going, without you physically needing to put in any additional energy. The other thing I want to emphasize here throughout this chapter, when we've been looking at enthalpy, we're not looking at rate. We're not looking at how fast the reaction occurs. So, not necessarily quickly. I mentioned rusting as an example. Nobody wants it to occur, but it just happens. It manages to steal enough energy from the surroundings, but it's a very, very slow process, a very, very slow reaction. Turns out to predict for spontaneity, both enthalpy and entropy are important. Enthalpy, we spent most of this chapter here on. Enthalpy was looking at heat. It's going to be sort of the energy change. The other one, which we spent just this half lesson on, entropy, turns out to be equally important. That's the amount of chaos, that's the amount of randomness that we have. Let's look at enthalpy first. For a reaction to occur, to just happen spontaneously, if I had a choice for heat, do I prefer the high energy side or the low energy side? Hopefully you were able to say to me here, an exothermic reaction should be spontaneous. Because if I write an exothermic reaction, that means I'm actually starting out high and I'm actually ending up at a lower energy state. So we're going to start out, I don't know necessarily how much energy the reactants have, nor how many my products have, but if over the course of the reaction, I fall from reactions to products, we're going to end up at a lower energy state. Lower energy, less can go wrong. It means it's going to be more stable. And it's true. A lot of exothermic reactions are spontaneous. Combustions just happen like that. You might need to spark it to get it going, but once the fire is raging, it just continues onwards, also very quickly. In grade 12, we're going to come back and we're going to correct this diagram a little bit here. It's not actually just simply falling reactions products. There always is an energy hill, but we've already assumed that it's stolen enough energy from the surroundings to get over that hill. That part there actually talks about the rate. It talks about how fast the reaction occurs. Entropy is a more interesting story. Turns out some exothermic reactions are non-spontaneous. Wait, the other side is more stable. Why don't I want to go that way? The other factor that I need to consider is this sort of half lesson that we did on entropy. And it turns out for entropy, there is something called the second law of thermodynamics. So now we have all the laws there. Second law of thermodynamics, there's a lot of different ways of writing it, but we're going to use this one way here. Second law of thermodynamics says that nature, or the universe, the nature always tends to greater disorder. So if it were up to the universe is naturally going to get more messy. It doesn't get less messy. So we can say that another way here. The universe entropy is always increasing. We see that with our rooms all the time. I'm sure nobody in their sane mind would be, oh, I want to make my room messy today. Right? It's just over time, you throw your shirt over here and you leave that your pants over there, your books over there. It just naturally tends to get more chaotic. Things don't naturally become more orderly. So the next time your parents tell you to clean your room, you can just be like, I'm obeying the second law of thermo. There's no fighting it. We're fighting this sort of depressing battle that nobody wins. There are some other interesting applications out of this. This actually explains why hot things get cold, but we're just going to use the lens of nature getting higher disorder. I'm going to do a little bit of hand-wavy math, and then we're going to flesh this out a little bit more in the next lesson. We're going to start off with the entropy change in the universe. The entropy change in the universe here, the universe is a huge place. I'm going to separate our universe into the system, our reaction, and the surroundings. And what the second law of thermodynamics guarantees is it says the entropy in the universe, the amount of disorder in the universe, is always increasing. This one here always is bigger than zero. We're always fighting a losing battle. I mentioned previously, entropy is a really hard concept to actually measure. We can sort of do this with dimensional analysis here. Entropy has units, joule per Kelvin mole. It sort of represents, yes, our randomness, our chaos, the amount of mess we have. It sort of has energy dependence divided by a temperature dependence. For the system, that's only a handful of particles in comparison to the rest of the particles in the universe. For the system, I can't use the following formula. However, in this case here, when I have my universe, again, this is just hand-wavy math here. So I have system, I have surroundings. Because my surroundings is actually humongous, as maybe I have a reaction that's endothermic or exothermic, as energy gets passed from system to surroundings, where my system may change temperature quite a lot, because my surroundings is the rest of the universe, because there's so much bulk material, I don't expect the temperature to actually change in the surroundings. So with that dimensional analysis in mind, with a little bit of hand-wavy math here, I'm going to give you one other formula. You don't need to derive this. I just want to show you where our last equation is going to come from. Delta S surroundings can be quoted as the negative of what's happening to the system. It's the opposite. It does track how much energy is changing from the system. Maybe it's lost or maybe it's gained. It has energy dependence on top, but it also has a temperature dependence on the bottom. So that's sort of the extent I can explain that part there. A little bit of hand-wavy math. I just want to show you a little bit of algebra when you punch it through that way. So if you just take my word for it for now, I know the entropy of the universe is always increasing, delta S universe. There's no changing this delta S system term, but I'm managing to actually quote, how does the entropy in the surroundings, how does the amount of chaos in the outside container, how does it change relative to what's happening in the system? So what I'm going to do here is I'm just going to punch in that term, delta H system divided by temperature. This one here always needs to be increasing. I don't necessarily like this divide by T. You can make a note to yourself, this is given. Right? I didn't pull that out of thin air there, so that's given. I don't like this divide by T, so what I'm going to do is I'm going to multiply everything by T. So T times delta S universe is equal to delta S system minus delta H. Sorry, I missed the T here. And this one here all has to be bigger than 0. So same formula, same sort of algebra. And as the last step here, I don't necessarily like having the enthalpy term second. So what I'm going to do is I'm going to pull out, I'm going to factor out a negative. Or the other way you can do is you can imagine multiplying by -1. If I multiply everything by -1, I get a negative T delta S universe. That's a big mess. A negative of negative becomes a positive. So I'm going to get a delta H system term come up front. This was positive beforehand, but now when I multiply by -1, I'm going to end up getting a minus T delta S term. And this is sort of the final way we're going to see this formula. What happens to an inequality, a greater than sign, when I multiply by -1? Hopefully you're able to say to me here, the greater than switches sign, it becomes less than. This one here is a huge mess. This one here, we're going to hide this mess, and we're going to call this a change in Gibbs free energy. So G is our last thermodynamic quantity here. Gibbs free energy. We're going to talk more about this in the next lesson. What does it mean, free energy? Gibbs actually relies on constant pressure. But basically, just big scale here, we know energy and entropy are important to figure out whether something is spontaneous or not. This formula helps us put in Here's the enthalpy argument. Here's the heat argument. Exo should be more stable. And here's the entropy argument. Here's the randomness argument. If these two numbers here, if they end up being less than 0, if the delta G is actually less than 0, both enthalpy and entropy are obeying the second law. That's going to mean spontaneous. If the delta G, however, is bigger than 0, it's going to be non-spontaneous. When it crosses over 0, we're going to see in tomorrow's lesson it hits equilibrium. So I'm going to just stop it there, and we're going to do one last lesson, and that'll finish off this chapter. Thanks, guys. Take care.